It is section 3.6, Parametric curves. Consider the data of form is given in this figure. For this data, none of the interpolation methods we have learned so far can be used to generate an interpolating curve, because the curve cannot be expressed as a function of one coordinate variable to the other. For example, if you consider the x variable as the domain, then we have two values at 0, so that it cannot be a function. Also, if you consider y as the domain variable, then again we have two value here, so that it cannot be a function. In this section, we will consider parametric curves in which we use a parameter to express both x and y as functions of the parameter. The general curves can be made in that way. For the data here, we introduce parameter here. In this case, now t is the parameter, and for the points, we consider in the beginning t is 0, and half, quarter, half, 3/4, and 1. Now we collect here x values from the data, -1, 0, 1, 0, 1, these x values, and now these are y values. So we may try to consider x as a function of t. T is moving from here there, and also y can be a function of t. Okay. Then here, using the parameter t, we get t and x paired, so that it's now domain, codomain, domain, codomain. In this way, we make a tx, and ty for y function, we try to get that data, and then we try to make, for each one, we try to get polynomial interpolation. Then here we can get plot. Okay, then here we can see this curve start from here and passing this point, and here again, and passing here now, and then coming over there. So it's a little bit oscillatory. So if we want to get such parametric curve, then we have to make it as good as possible, and particularly it should not be oscillatory. Here, in reality, it is applied for computer graphics, and the requirement is rapid generation. Once you try to get curve, then you have to do it very effectively, and so that the required thing is rapid generation of smooth curves that can be quickly and easily modified. And preferred is a change of one portion of a curve should have little or no change on the portions of the curve. I said here preferred, however, in fact, this is also required. So once you try to make long curve, and one part is touched, then if the other part is also affected and changed, then it'll take really long time, and you have to do it many times of iteration, and it's not really rapid generation. For these two requirements, the choice of curve is a form of the piecewise cubic Hermite polynomial. For x function, for y function, both of them, we try to make a piecewise cubic Hermite polynomial. For example, here, the data is given in point, and the function value at the point, and then derivative value given, then the piecewise cubic Hermite polynomial can be generated independently in each portion. In each subinterval, you can construct the curve independently here. Let's see why it is happening. Now there is x0, and there is x1 and x2. Okay. Then in the beginning, the value at x0 and slope is given, value, slope. And for each point, in fact, the value, slope is given. Then by using here information, value, slope, by using 4 information, you can get cubic Hermite polynomial. So satisfying this value and slope, it can be made here. Now, again, we are using the same value, same slope, and try to make the second portion so that it is made that way. Now, here, even though you change this one, for example, like that, and value and slope, then here start with the same value, same slope, and going up and moving that way. So here, this portion is not really affected. So piecewise cubic Hermite polynomial is really the choice. Okay. Okay, here, now we'll consider how to get piecewise cubic Hermite polynomial for general curve fitting. Because you can construct the curve part by part, we may now focus on the first portion of the piecewise cubic Hermite polynomial and interpolating between x0, y0 and x1, y1. And here, now, but here data will be given in this way, even though you introduce time, so that time here is 0 and time here is 1. Well, then now we have, that is for x variable, x at 0 is x0 and x at 1 is x1. Now for y variable, here y at 0 is y0 and y at 1 is y1. Now assume we have for x0, y0, we have a slope. So here that is x0 and y0. That is x1. That is x0 and that is x1. And here y0 and y1, we have slope here. And now along with time t introduction, we have here for the equation, and then this slope at 0 and the slope at 1 are given, so that we have only 6 conditions. Now, however, if you try to get x as a function of t and y as a function of t, must be, you have to construct 2 polynomials, but each one requires 4 conditions, so that total a is required. For example, for x construction, you need a value at 0, value 1 is already known, but for that portion is not yet known. And also the same for y function, you have to get y values at 0 and 1, okay, these are given, but for y prime at 0, there's now time is 0, and y prime at 1 is, these two are not given. We have only 6 conditions, but we need to get 8 values, 8 information, so that we have to do a little bit of manipulation. That begins with this identity, and dy over dx, that is slope, and here y change with respect to x. So that is naturally given. However, once xy are function of t parameter, then it can be written as y prime t over x prime t. So rather than this one at 0, we may get here two values if one is separated into two values. So that in the beginning, it looks very ambiguous. However, this ambiguity can be considered as a flexibility for the construction of parametric curves. We'll see how this ambiguity is changed into flexibility. Okay, here now dy over dx is given. Okay, we'll come back to the concept of guide points later on. Now dy over dx at t equals 0, which means that the slope over there can be considered as, now by using this formula, y prime at 0 times 0 and x prime 0. Now we'll call this portion as beta 0 and that portion as alpha 0. Now that is along with the guide point concept. Okay, we'll try to separate one value, given value, into two portions. And now at 1, the slope, that is pictorially this one, the slope. Now for the slope, we try to make two values so that we call them beta 1, alpha 1. Okay, momentarily, let's accept that. Then, and we have now total A, because we now specify this the values so that eventually now everything is given. Okay, here, so with that, here now the Hermite cubic polynomial can be constructed. Now at 0 and the value, x value, and the derivative value, x prime at 0, and at 1, now value, x value, and its derivative value. By using that, the formula, cubic Hermite polynomial, can be gotten by using this formula. Similarly, now for y function, here y0, y prime 0, and y1 and y prime 1 are given, then the formula for the cubic Hermite polynomial can be given in this way. Okay, let's see this example. Here, x0, y0 is 0, 0, and at t equals 0, the slope is 1. Now, here, x1 or y1 is 1, 0, and at the point, the slope is minus 1. Okay, let's try to visualize it. Here now is 0, and now again, okay, x0, y0 is 0, 0, so at that point, in this y, okay, let's try to make here y-axis. That is now y-axis. The first point is this one, and last point is this one. That is 1, 0, that one. Now slope at the point is 1, that is slope, and slope at this point, okay, that is 1, is minus 1, like that, right? Okay, so we have right now 1, 2, 3, 4, 5, 6 information. Now from this one, we try to get, okay, 1 dy over dx can be written here 1 over 1. So alpha 0 is 1, beta 0 is 1 from this one. Now from that one at t equal 1, which is minus 1, that can be written now minus 1 over 1. So we try to get that one. Looks like very ambiguous at this moment, but later on it'll be quite clear. This is quite flexible later on. You can see it sooner or later. Okay, so we have a total 1, 2, 3, 4, 5, 6, 7, 8 information. Now we collect for x function. Then here x at 0 is 0, and at the moment the slope is 1, x at 1 is 1, and slope is 1. Along with these 4 conditions, by using that formula, we can get the polynomial, cubic polynomial. That is now happen to be just a linear function. Now, if we collect y information for y, then y0, the value is 0, and the slope is 1. At 1, the value is 0, and slope is minus 1. And with that information, we can get here this one. Okay, put together and function of x function, y function, and try to make a plot. That name is h1. Now, for the same data, rather than here for 1, here 1 over 1, we may try to get 0.5 over 0.5. Also over there, rather than minus 1 over 1, we try to get minus half over half, so that eventually the ratio becomes minus 1. So that is the second choice. Here, half over half, which is 1. Now, minus half over half, which is minus 1. Along with this choice, now we collect for x function and y function. Then here, x and y are made. And for this pair, we make a plot which is h2. Now here we see the plot. Okay, and for the first h1, here the slope is now slope is 1. We are using over there, that is 1 over 1. For this one now is in fact half over half. Right? In this plot, h1 is this curve, and h2 is that curve. So it is related with the guide point, and guide point can be picked, and there's 1 over 1, that slope, and length is 1, x direction 1, y direction 1, so that if you choose guide point for here for the slope, and for the right end point is minus 1, look at over there, there's a minus 1 over 1, in y direction minus 1, in x direction 1. Okay, in y direction is going down, in x direction positive, so that for the value minus 1 for here, now you have to choose the top minus 1, the minus value, negative value, bottom positive value. So that's the reason we chose here minus 1 and 1. Okay, so geometrically it's quite clear. If you choose this one as a positive value and negative, then you are wrong, because it's going down, so that y change is negative, and now because it's moving in the x direction, right direction, so that x prime must be positive and y prime must be negative, right? Okay. So here now, for this one, guide point is this one, and for that point, the original guide point is that one. Okay, so that 1, 1 guide point must be over there. Okay, then you can make this one. If you are choosing guide point half and half like that, and over there half and half, then it is now here flatter. So if you want to make sharper the curve, then you may try to choose long guide points, and then the curve is following the long guideline in better. If it's short, then, for example, small, then it's almost flat and touching this axis. In this way, you can choose the guide point, and then, and with a long guide point line, you can make the curve fitting what you need. And here, but in practical software like Maya is one of the popular graphic tools. If you are using Maya, then for here guide point you have to choose this one, but for that direction you may choose guide point that one. The reason is that if you try to choose guide point that way, then it's outside of the graph, so that to make it inside here for that one here now in the up, so that it is inside of the graph, so you can choose guide point over there. Okay, but originally mathematically the guide point must be chosen over there, so that start from here and now go down that way. Okay. Okay, that is the materials, and for this chapter, the last problem is about the parametric curve. Now for circle, okay, we chose here circle of radius 1. Now we chose here point here and point here and here, so that to reconstruct the circle, you have to make this portion, that portion, and this piece. By constructing 3 pieces, we may try to get a quite good circle. This is an example, so that by using a simple choice for the slope and alpha and the beta values, I made that one. But if you spend more time and try to get alpha values and beta values better, then you can make really very good curve, and it really looks circle. And now in the choice, look at here. Now at the point, slope is infinity. dy over dx is infinity. And here, that is the direction. Okay. So for that one, okay, let's try to make the picture a little bit better. Okay, here now, the slope is infinity like that. So that is dy over dx, that is infinity. So here, for that point, x prime must be 0, and y prime here 0 at must be positive, because in y direction is increasing. So that is here now alpha 0 is 0 and beta 0 is 1, representing that one. At the point for this curve, at the point now the slope is 0. But for that one, so that dy over dx equals 0, but here x prime at 0 must be negative, but y prime, okay, in fact this is 1 now, from 0 to 1, y prime at 1 must be 0. In y direction no change, but x direction is decreasing, so that must be negative. So that's the reason here I chose alpha 1 is minus 1 and beta 1 is 0. Okay? Now, that is a hint for the construction of this portion and that portion. If we are choosing these alpha values, beta values quite nicely, then eventually after combining these three pieces, you can see really almost the same as the circle of radius 1. Okay, this is end of the section and end of the chapter. Thank you.